I'm Marin Francesco and I will talk about polymorphism of perylene diimides, their thermal and mechanical analysis, and the role of the alkyl chains. PDIs are N-type molecular organic semiconductors which possess an excellent chemical and thermal stability. They have potential application in devices such as organic field effect transistors and solar cells. They are not expensive and they are commercially available. Even though there is an extensive literature describing their optoelectronic characteristics, little attention has been paid on their structural characteristics and on their polymorphism. For this reason, we decided to work on 4 different PDIs functionalized in a symmetric fashion with alkyl chain of different length, ranging from 5 carbon atoms to 8 carbon atoms. First, we started with the thermal characterization of these compounds, and we found from TGA that they are thermally stable up to 400 degrees. By DSC, we found out that we have several transitions with temperature, which seems to be reversible upon cooling. For this reason, we decided to perform variable temperature X-ray powder diffraction to follow the structural variation upon temperature. In case of PDIC8, we observe a shift of the peaks due to thermal expansion up to 200 degrees, so just before transition. At 240 degrees, we observe the formation of form 2, and this transition is completed at 275 degrees. When we cool down to room temperature, we observe that all the form 2 is converted to form 1. In case of PDIC6, we observe a similar situation. We have thermal expansion effect up to 175 degrees, and then formation of form 2 and form 3. In this case, new peaks arises which are not ascribable to form 1 upon cooling to room temperature, which means that maybe not all the compound revert back to form 1, or we have formation of new polymers, which suggests the possible presence of different transition pathways. In order to investigate on the polymorphism of these materials, we decided to perform a polymorph screening. However, the number of available techniques for PDIs are very limited due to their very poor solubility. Anyway, we found in solvothermal crystallization a way to obtain nice single crystals. For crystallization, we used the solvent dichloromethane, chloroform, and toluene and paraxylene. With the crystal obtained in this way, we performed the hot stage microscopy in order to follow the transition observed in DSC and variable temperature X-ray diffraction. At first, with PDI6, which is very similar to C5, we observed the elongation of crystal due to thermal expansion. And the first transition occurs with the front of transition very clearly visible, and it was quite single crystal to single crystal-like. Then we have the second transition, and then when we cool down to room temperature, we observe the reverse transition with a thermosilent behavior. In this case, the crystal didn't jump because there was placed above them the cover slip. In case of PDIC7 and C8, the behavior was a bit different compared to PDIC6 and C5. Here, the transition was not single crystal to single crystal, but the crystal tend to break apart and delaminate. When we cool down to room temperature, also in this case, we observe the reverse transition. The crystal obtained by solvothermal crystallization were then analyzed by single crystal X-ray diffraction and mostly resulted in form 1 of the PDIs. PDIC7 form 1 is a new crystal structure, while the other ones were already present in the CST database. However, we decided to collect all of them at room temperature in order to compare the crystal structure. All of them presented the same packing motif, which is a monodimensional lamellar packing motif. In this case, we have pi-stacked columns of molecules, in which the distance between molecules is the A-axis. In fact, it's very similar in all the crystal structure. Also, the B-axis is very similar because it's the distance between two neighboring columns of pi-stacked molecules. The columns are linked together by weak CHO hydrogen bonding interaction. The difference between the crystal structure can be observed by the z-axis and the volume of the unit cell, which depends by the length of the alkyl chain. In fact, we observe the z-axis is longer for PDIC8 and the volume is higher. PDIC7 possesses a very small difference compared to the other structure. In fact, in this case, we have the terminal carbon atom of the alkyl chain, which is disordered in two positions with a static disorder. From solvothermal crystallization of PDIC5 in toluene and paraxylene, we obtain a new crystal form stable at room temperature, which corresponded to a solvate. In fact, in the crystal structure, we observe some void channel of volume approximately 14% at 200 Kelvin. In fact, we have a longer z-axis and a higher volume compared to form 1 of PDIC5. To verify the presence of solvent, we did a hot state microscopy with the crystal immersed in oil, and we will see bubbling formation due to the solvent leaving the crystals. Since the solvent tend to go back to form 1 upon grinding, we found that the ratio between PDIC5 and solvent molecules to be 1 to 1 by HNMR. After this, we decided to investigate the mechanical properties of these PDIs by subject them to bending tests to see whether they exhibit brittle, plastic, or elastic behavior. When we apply a deformation perpendicular to the 010 phase, the PDIs exhibited brittle behavior. Then, with the aid of the software Crystal Explorer, we correlate the brittle behavior with the crystal structure of the PDIs by using the tool of energy frameworks. Energy frameworks allow us to calculate the interaction energy between a molecule and its nearest neighbor, and is displayed with tubes of different thickness. The thicker is the tube, the stronger is the interaction. In this case, we have a 2D network of strong interaction ranging from 30 to 120 kJ per mole, and these interactions are mainly due to pi stacking and CHO weak hydrogen bonds. These 2D networks give rigidity to the crystal. In fact, when we try to deform the crystal by applying a force perpendicular to the 010 phase, we try to deform this 2D network, and it results on the crystal breaking. Instead, when the deformation is applied perpendicular to the 001 phase, we have the PDIs exhibit elastic behavior. In fact, we are able to deform them, and then they just come back to the initial shape. Again, the behavior was correlated to the crystal structure using Crystal Explorer and energy frameworks. In this case, we have a region of weaker interaction from 3 to 5 kJ per mole that correspond to the alkyl chain region. So this region of weaker interaction gives flexibility to the crystal. In fact, that's why when we apply a force perpendicular to the 001 phase, we don't have brittle behavior. However, to us it's not completely clear why we have elastic behavior instead of plastic, whether the reason is that the molecules are just able to reorganize reversibly or because of interdigitation of the alkyl chain. In conclusion, we observed several high-temperature crystal forms which were reversible in some cases and not completely reversible in others. We observed the effect of thermal expansion and the thermosalient effect in some crystals. Despite very similar packing characteristics with the same crystallization technique, only PDIC5 was able to form solvate. This might suggest a particular affinity of the pentyl-alkyl chain for toluene and paraxylene. PDIs also exhibited anisotropic mechanical properties, and we were able to correlate the mechanical behavior with the crystal packing characteristics. The displayed elastic behavior is a very important feature for development of flexible devices. I want to thank the research group, my supervisor, Professor Lucia Maini, and my master thesis, Roberta Versa. And also I want to thank Giovanni Crystallografi Italiani to allow me to give this talk. And thank you all for your attention.